This video will serve as an introduction to water chemistry that we'll use as the basis for all of our field methods instruction in water chemistry. We're going to talk through different groups of analytes and different groups of parameters that we would use to monitor different things. The purpose of this is just to talk through why we would monitor things, how we sample for them, and some of the parameter-specific information that we need to be able to plan our sampling. So we'll talk about field parameters, which are things that we measure in the field, metals and other cations. So cation means a positively charged ion. So most metals are cations. We'll talk about nutrients. Nutrient pollution is a major issue in water quality right now. We'll talk about anions, which are negatively charged ions. Different categories of organic constituents. So here they're grouped by their volatility, which means the ease at which they evaporate. We'll talk about bacteria and pathogens and how we sample for those, and then how we sample for solids and sediments. So we're going to go through just some very basic chemical principles that will help frame this information. So one of the most important things to remember is that water is what's called a polar solvent, which means that it's positively charged on one side and negatively charged on the other. That makes it a universal solvent. So many things will dissolve into water, which is why sampling water is very important. How much of a metal will dissolve into the water depends on pH. So in general, more metals, a higher concentration of metals, will dissolve in water at a lower pH than a higher pH. Depending on the pH as well, anions will bond with different metals depending on the pH. And so we would expect to see different compounds forming, different compounds forming with metals bonding to anions depending on what pH the solution is. Typically or often, organic molecules don't dissolve in water because many of them are what's called nonpolar. So they don't have a positive charge on one side and a negative charge on the other, which means that they don't dissolve easily in water. And then volatile compounds, these are compounds that evaporate very easily. They don't necessarily stay dissolved in the water if there's any agitation or oxidation because they evaporate out of the solution very easily. Other things to remember are that pH and dissolved oxygen, which are two of our really standard field parameters that we measure at almost every site, they're dictated by temperature. And so we can't leave water sitting in a bucket in the sun, for example, and expect them to stay the same. After we take the sample and that sample is in a bottle, we also need to understand that things are going to continue to change, and we need to try to preserve the sample to limit how much that sample changes. So for example, metals will oxidize. They'll react with oxygen in the bottle and in the sample, and that can change the pH, it can change the acidity, the alkalinity, the solids levels, it can change the concentrations of different parameters, including metals and anions as things bond to each other. So when we take samples and when we preserve samples, we have to keep this in mind so that we try to keep the sample as close to what was in the stream as possible. So when we talk about field parameters, these are things that would likely change between the field and the lab. So they're things that we measure in the field so that we measure them as close to what they are in the stream as possible. So the primary field parameters that we talk about, and we'll group these together and we'll say field parameters pretty often, are pH, dissolved oxygen, specific conductivity, oxidation reduction potential, temperature, and total dissolved solids. And we'll talk about each of these individually in a moment. When we talk about metals and other cations, these are positively charged ions. In general, the solubility goes down as the pH goes up. So what that means is that less of those metals can be dissolved in the solution as the pH rises. So you'll have a higher concentration dissolved in the water at low pH and a lower concentration dissolved in the water at high pH. In order to keep metals in solution, so when we take a sample and we want to analyze for all of those metals, we want to try to keep them in solution so that we can analyze all of them. So in order to do that, we preserve them with acids. We drop the pH low enough that those metals want to be dissolved in the solution instead of precipitating out and becoming a solid. So in general, we'll use nitric acid for most samples. That's going to be kind of the standard acid preservation that we'll use. If oxidation state matters, so metals can come in different oxidation states. So you may have seen iron with a +2 charge and a +3 charge, or aluminum with a +2 charge or a +3 charge. And all that means is the number of electrons that are bonded to that metal. But that can be changed in solution. So iron with a +2 charge can be oxidized to a +3 charge. So if we care about that speciation, whether we have iron 2 or iron 3, we have to use hydrochloric acid to preserve that sample, and even then it may not totally preserve it. It's better to analyze that in the field if you have equipment that can do it. If you don't have equipment that can do that, then we use hydrochloric acid because hydrochloric acid tends to not oxidize the sample. If we're analyzing for nitrogen in a sample and we need to preserve it, so if we're looking at, we'll talk about this in a little while, but if we're looking for total nitrogen or ammonia or nitrate or nitrite, then we don't want to add nitric acid because that will add nitrogen to the solution. And so we would use sulfuric acid instead. So for our metals and our other cations, acid preservation is going to be our best strategy for keeping those in solution. With the anions, we're targeting things like sulfate, chloride, bromide, nitrate, carbonate, things like that. So these are all negatively charged ions. So when we look at ionic chemistry, we'll have these positively charged metals and other cations, negatively charged anions. When they're in solution, they're not bonded to each other. But then depending on the chemistry of the solution, they may bond to each other and either stay in solution, stay suspended in solution, or become a solid and settle out to the bottom. So typically, in our samples, these are much more stable and less likely to precipitate out easily than our metals, because our metals will bond with oxygen, or will oxidize and become oxides and hydroxides. Those reactions will happen much more than reactions with these. So in general, for most of our anions, we preserve the sample by removing oxygen, so by purging the container of oxygen, and by keeping it cold. Nitrate and nitrite may still need to be preserved, like I spoke about on the previous slide. Preservation with acids tends to interfere with these readings. For example, sulfuric acid would add sulfate, hydrochloric acid would add chloride, nitric acid would add nitrate, or would interfere with nitrate. So we don't preserve with acid. We keep these samples below 4 degrees Celsius, and we force all the air out of the sample to limit oxidation. When we talk about organic chemicals, these chemicals are defined by their content of hydrogen and carbon. So organic chemicals are chemicals that are based on a carbon and hydrogen formula. And so these are things like methane and butane and propane. They're also things like gasoline and byproducts, and oils and byproducts, and benzene and toluene. So these are things we see across a wide variety of industrial processes, but also natural ones. So depending on their structure, they may or may not dissolve in water. And so if they don't dissolve in water, they may either be heavier than water, which means they'll sink to the bottom, or lighter than water, which means they'll rise to the top. So like you've seen oil sheens on water, those are compounds that are lighter than water, and so they're rising to the top. Those that will dissolve in water may be volatile, semi-volatile, or non-volatile, and this volatility refers to how easily they evaporate out of the water. So volatile chemicals will evaporate very, very easily. Semi-volatile ones would require either more agitation or a higher temperature to evaporate, and non-volatile ones would take a very high temperature to evaporate out of a solution. And so we try to sample these with no air in the container, especially for volatile compounds. And those are often what we're measuring. So methane, benzene, toluene, ethylbenzene, and xylenes are the most common ones that we'll sample for. and those are very volatile, so it's very important that we remove all the air from the containers. We try to keep those samples cold. Chemical reactions tend to happen slower when it's colder, and volatile compounds will be less volatile at a low temperature than a high temperature. If you imagine boiling water, as you heat it, you'll have more and more evaporation. It's the same thing with these. Higher temperature will mean more volatility. Some of these may be preserved with hydrochloric acid. It tends to help stabilize things. But really, the most important thing is that you have to know what you're looking for and what you're going to analyze for and what the properties are of that. And there are specific sampling protocols depending on what exactly you're sampling for. And so this goes back to understanding the purpose of your sampling, what you're sampling for, and why you're doing it, so that you can go back and figure out exactly what protocol you need to use. When we talk about bacteria and pathogens, the first thing that we need to consider is our own personal safety. And so wearing appropriate protective equipment, gloves, goggles if there's going to be spray, ensuring that you wash your hands before eating, things like that is really important. Typically these aren't preserved, but they have a very, very short holding time. So we talked about holding time previously, but holding time is the time between sampling and analysis, the allowable time between sampling and analysis. So with bacteria and pathogens, this is typically less than 6 hours. And then the sample needs to be kept cold. Bacteria and pathogens will multiply at a higher rate at a higher temperature. And so by keeping this cold, you can keep it more similar to what was in the stream than if it gets warm, and then you'll have a lot of bacterial multiplication. And this has to be sampled, or this has to be analyzed quite quickly to make sure that you're representing what was in the stream. This is a parameter that is very, very variable. Over time, there are just so many variables that affect the bacterial level in a creek, and so this has to be sampled more than once for a good result. So depending on what sampling protocol you're following and the purpose of your sampling, often what's recommended is 5 samples within a 30-day period, trying to cover the variability in flow regime over that 30-day period. And then based on those results, you can say that something's exceeding or not exceeding the standards. For solids, both total dissolved and suspended solids and total solids can be tested in the lab. And these are tested using fully physical methods, so through evaporation and filtration and then weighing those remaining solids. And so there's no preservation needed for these samples, but typically we'll purge air out of the sample, and keep it cold. It'll be the same sample container that we use for our anions often. And so this is tested through filtration and evaporation. So, the dissolved solids are the ones that pass through a filter. So then all the water is then evaporated off and then weighed. For total solids, the whole sample will be evaporated off, and the solids will be weighed, and then the suspended solids are the difference between the two. So those are the filterable solids. And typically this is done with a filter size of 0.45 microns. So everything that's suspended in the water that's of a size greater than 0.45 microns would be considered suspended. Everything smaller than 0.45 microns would be considered dissolved. Right, so depending on what parameters we're analyzing for, we'll also use different types of bottles. So most samples will use plastic bottles. So these will either be flexible or rigid plastic bottles. We'll demonstrate multiple types in class. We'll use these for most samples, except for things that are highly corrosive or are organic compounds. Those organic compounds may or may not be chemically similar to the plastic that's in the bottle, and so we don't want to have any possibility of contaminating our sample with what's in the bottle. We'll use glass bottles for things that are corrosive or for organic materials. We can also have either amber or clear bottles. So our amber bottles are tinted brown essentially, and those are meant to limit UV light penetration. So UV is an oxidizer, so if we have a sample where we're trying to limit oxidation of that sample, we'll use an amber bottle to limit penetration of UV light into it. We'll use clear bottles for things that are stable in UV light, so things where we're not worried about the oxidation state of what's in the bottle. We can also use a flexible bottle. I'll demonstrate these in class. The type we use the most often are called Q-attainers, and we use that to be able to force all of the air out of the samples, where that's one of our preservation methods. There are also lids with septums, and we'll demonstrate these in class, but the septums allow an autosampler on a GCMS, which is a piece of analytical equipment used to analyze for organic compounds. Then an autosampler can pierce that lid so that you never have any contamination or exposure to oxygen. And so this can be really good for volatile organic compounds where opening the bottle may affect what you get in the bottle. Finally, when we take our samples, we need to think about filtration of those samples as well. So we use filtration to determine what's suspended versus what's dissolved in our sample. We may also use filtration if we have particularly sensitive analytical equipment that can't have solids running through it. So typically we'll use a 0.45 micron filter. This is standard for most applications. It has a pretty high flow rate in the field, so it's not too burdensome for the field, for whoever's taking the field measurements. There is some discussion in the literature, however, about whether a 0.2 micron filter would be a better application. Some studies are showing that the truly dissolved fraction is actually much smaller, and that we're missing things with this kind of coarse metric of a 0.45 micron filter. But it's a much lower flow rate in the field. It's a lot harder to do. It takes a lot more pressure to get the sample through that filter. And it's very, very difficult if you have a lot of solids in your water. So a lot of places where we either have a lot of sediment, or in our mining applications where we have a lot of metals in the water, this can be very, very difficult. So typically in the lab we'll analyze a filtered sample and we'll analyze an unfiltered sample so that we quantify our total versus our dissolved constituents. What we have to remember though is that this doubles the price of our analysis. So we have to think hard about whether our sampling plan and whether the purpose of our sampling requires filtration or not. So that's the end of this video about our introduction to water quality sampling. In the next video we'll talk about specific parameters one by one to get that background before we go out in the field. Thank you for listening.